Okay, so today we're going to talk about higher order derivatives. And what this simply means is not just simply taking a first derivative, because that's what a derivative all it is. It's just simply the first derivative. We can take second derivatives, third derivatives, fourth derivatives, and so on. And that's what we're talking about. If you have your first derivative by taking the derivative of the function, you can take another derivative after that now becomes the second derivative of that function. And if you take the derivative of the second derivative, well, that now leaves the third derivative, and then so on and so forth. So we can keep on going until either we get to a constant function 0, or until we get to the point where we want to stop anyway. Polynomial functions will eventually yield, at some point down the line, a derivative that gives you a function that is just simply 0. If you're talking about square roots, exponentials, other functions, we can go further than that. So, let's find the second derivative. So here's my function. X to the fourth plus 2x cubed minus 3x squared minus x. So my first derivative, well, derivative of x to the fourth is 4x cubed, and then 6x squared, and then 6x, and then 1. The second derivative, which we'll notate by doing a double apostrophe, so we call this actually prime, so it's f prime is the derivative, f double prime now is the second derivative. Well, derivative of 4x cubed is now 12x squared, and then 12x, negative 6. The 1 now goes away, and it's gone. So there's our second derivative. I can keep on going. I could take a third derivative, and then the fourth, and then a fifth, and stop whenever I wanted. But for this problem, we're going to stop at the second derivative. Now here we have f of x equals x sine of x. So we have our product rule. Well, I can still use the product rule to find a second derivative. I can just keep on going. So our first derivative of the first expression is 1, so it just becomes sine of x. And then plus x times the second function's derivative is cosine of x. So there's our first derivative. Well, let's find a second derivative now. So, derivative of sine is just simply cosine. Now we have another product rule, x cosine of x. So the derivative of the first function is 1, so it's plus cosine of x. And then plus x times the derivative of the second function, which is negative sine of x. Well, when I combine like terms properly, I get 2 cosine of x minus x sine of x. And that right there is the derivative, the second derivative of the original function x sine of x. Again, I can keep on going. I can take a third derivative, a fourth, a fifth, and so on as far as I wanted to. Now, sometimes you'll be given an original function. They'll tell you it's for up the bat to find the second derivative. They'll just find a higher order. So in this case, it is a second derivative, f double prime of x. So the first derivative is 2x. Second derivative is just simply 2. As far as it goes. No big deal. For this particular problem, notice we're starting with the third derivative. It's 2 times the square root of x. We want to use that now to find the sixth derivative. And that's what this little symbol right here. It's not saying f to the sixth power, it's saying the sixth derivative of f. So I can't just keep on using primes. I can't just have like 20 primes and say it's the 20th derivative. I'd rather write f 20 power like that. So the first thing I want to do is first I'm going to rewrite the third derivative as 2x to the 1/2 power. Whereas in exponential form, so when I take my derivative, it's much easier to work with. So the fourth derivative, so I multiply the exponent, 1/2 times 2 is 1, so it's x to the negative 1/2 power. I now find my fifth derivative. So the exponent goes in front, negative 1/2. I decrease it by 1, so it's negative 3/2 now. And now I take the derivative again to find the sixth derivative. So I do negative 3/2 times negative 1/2 and get a positive 3/4. I again decrease the exponent by 1. So the sixth derivative of this function, whatever it was, because I don't know what it is originally, I only know the third derivative, is 3/4 x to the negative 5/2. We will eventually learn how to find stuff like the original derivative for this function. That's what we call integration. That is a much later chapter, but we will eventually get to that, the whole reversing the derivative process. So there we go. Not that bad. Now, as I talked about before, when we talked about position and velocity, the acceleration function is also related to this stuff. Acceleration is found by taking the derivative of the velocity function. And since the velocity is the derivative of position, this means acceleration really is the second derivative of that position function. So if a of t is the acceleration, that means it's the derivative of velocity, which is the second derivative of position. So I can use this information with, again, my free-falling problem, or with any other time I'm given position functions to work with and actually find acceleration. So if I went back to that original problem that we talked about, when is the we had the situation you were jumping off a diving board, I could have talked about, okay, when is the acceleration 0, or when is the acceleration equal to 5, stuff like that. For this problem, though, I'm not going to be given position. We're going to just work with velocity. So we're told the velocity is given by v of t equals 500t over 3t plus 4. Now I want to find the acceleration after 1 second, 5 seconds, and 9 seconds. Well, in order to find these accelerations, I need to find the acceleration function, which means to take the derivative of the velocity function. Now there's my velocity function right there. Well, this is now going to be a quotient rule like we dealt with last time. So our acceleration, since quotient rule, it's the derivative of the top, 500, times the bottom. And please be very careful with how you write your t's so that it doesn't look like plus signs. You've got to be very careful with that. Minus the top function times the derivative of the bottom function. All divided by the bottom function squared. So up top, we're going to get, when we distribute, 1500t plus 2000 minus 1500t all over 3t plus 4 squared. So this, when you combine everything properly, will just simply become 2000, because the 1500t and the negative 1500t will cancel out, over 3t plus 4 squared. So we had to find the acceleration function first to actually apply and answer the question. I now want the acceleration after 1 second, 5 seconds, and 9 seconds. Well, I need to find a of 1, a of 5, and a of 9. Which means I'm plugging 1 in for t, 5 in for t, and 9 in for t and solving out the problem. So for this particular example, if you left it in fraction form, it would be 2000 over 49. And then the units would be feet per second cubed. Acceleration is always the length over the time units squared. For 5, it would be 2000 over 361. Again, feet per second cubed. Sorry, squared. And then finally, when you plug in 9, you get 2000 over 961 feet per second squared. If you wanted to write them as decimals instead of fractions, no big deal. The first one would have been 40.816, again the same units. Second one is 5.540, and the last one is 2.081. You notice for the most part I always have 3 digits after the decimal point to write my final answer. It's how I wrap it. It's how I expect my students around it, but if you're in other classes, you do as your teacher tells you to. That's how we find the acceleration. It's always the derivative of velocity. If I'm given position, I take 2 derivatives to get down to my acceleration, and then answer the problem from there. Okay, so that's the concept of higher order derivatives. All it is simply taking derivatives again and again and again. So all the different power rules, product rules, quotient rules, all those rules still apply. You're just now thinking of the derivative function, the first derivative, as now a new function, and taking the derivative of that to find the second derivative. Okay, so next time we're going to talk about another type of rule, the chain rule, for dealing with even more complex derivatives of functions. So I will see you next time.